Coming at you live from Funfetti Studios, it's alcohol reactions. A look at Sn1, Sn2, E1, and E2 reactions. Let's get started. First, let's talk about some generalizations when predicting the reaction type to expect. When we look at our alcohols, if we react them with one of our binary acids, HCl, HBr, or HI, those are going to lend themselves well to a substitution reaction. So if these are the reagents we're using, we can expect an SN reaction for each of these types of alcohols, primary, secondary, and tertiary. And what will a substitution reaction do if we have an alcohol? Well, it's going to leave us with an alkyl halide. Now then, the type of substitution that will occur, or that we expect at least, can be dictated by the type of alcohol we're looking at. So, as we'll take a closer look at in a moment, primary alcohols, if we were to try to proceed through a carbocation intermediate, we would create a primary carbocation, which is terribly unstable. Therefore, these do not lend themselves well to Sn1 reactions. Instead, we would expect an Sn2 reaction to occur. With that being said, secondary and tertiary alcohols, well, they would form secondary and tertiary carbocations respectively, which are substantially more stable. So these will tend to proceed through the Sn1 reactions. Okay, well, what if our reagent is H2SO4, sulfuric acid, and heat? In this case, we would expect our alcohols to undergo an elimination reaction. So an E type of reaction, regardless of if it's primary, secondary, or tertiary. Once again, the same rules for dictating which number, 1 versus 2, apply. The same that we used for the SNs can be used here. So a primary alcohol, because a primary carbocation is not very stable at all, we can expect this to go through an E2 mechanism. Whereas the secondary and tertiary, we would expect E1. And the results of these are alkenes. So, with that being said, let's take a look at each of these different classes of reaction. Sn1, Sn2, E1, and E2. Let's talk about predicting the products and the mechanisms involved. On this first one, we can see that we're reacting our alcohol with H2SO4 and using heat as well. So, since we're using H2SO4, we can reason that we're going to be looking at some sort of elimination reaction. Cool. But what number? I'm glad you asked. Looking at our carbon, we can see that it's a secondary carbon that the alcohol is coming off of, so this is a secondary alcohol, which means this is going to be E1. Cool. So this can safely proceed through a carbocation intermediate. When predicting the products, the key comes down to the intermediate. And so since we know this will proceed through a carbocation, let's draw what the carbocation intermediate would look like. So it's essentially going to be the same structure, wha-pow! Only instead of an alcohol, we will have a positive charge. So this is what our initial intermediate would look like. Well, first we'd have a water leaving group, and then after it leaves, this is what our initial carbocation intermediate would look like. The first thing I like to ask myself is there a viable position for a hydride shift? So here again, this is a secondary carbocation, right? So we just want to see, is one of the neighboring carbons a better place for the positive charge? Well, we have this carbon, which is primary. I should think not. And we have this carbon, which happens to have hydrogen on it, but is tertiary. So a tertiary carbocation is more stable than a primary, or than a secondary carbocation, well, and a primary carbocation. So a hydride shift is indeed in play. So we could have this intermediate that we've drawn, or this intermediate here afforded by the hydride shift. Since both are viable intermediates, both can lead to elimination products. So let's go through the 4 different products we can expect from this. The elimination reaction leads to the formation of a double bond. One of the carbons involved in the double bond will be the site of the carbocation. So for this intermediate, if we form a double bond elimination product based off of it, one of the carbons involved in the double bond will be right there. All we have to do is look next door and see if there is a hydrogen that we can take. If so, we can form a double bond product, an alkene product, based off of that. So, if we look at this carbon, does it have a hydrogen we can pull? Well, yeah, it actually has 3 hydrogens, right? So, as long as there's 1 hydrogen, this hydrogen can be pulled off and lead itself to a double bond. We'll do the mechanism in just a moment. That would lead to this minor product. So we've got the double bond there. Actually, let's make it look a little bit more obvious. Okay, so that is product number 1. We can take the same logic, and instead of abstracting that proton, we could take one from this carbon, which also happens to have a hydrogen. And if so, our double bond would end up here. So that product would look like this. Okay, so those are the 2 possible products we could get from our initial secondary carbocation intermediate right here. Now, let's see what our tertiary carbocation intermediate can afford. We could take a proton from this carbon, because it has a proton that can be abstracted, which would collapse the double bond right into here, which would give us this, which is also a minor product. Well, when are we going to get to the major product? Answer, right now. So, what if instead we took a proton from this carbon right here? So, it's got a proton available on it. We could take it and make a double bond right there, giving us this, our 4th and final product. This one is also the major product. What is it about this product that's so special? Well, we can use Zaitsev's rule. And Zaitsev's rule says if we look at our alkene, we want to look at the number of carbons that are branching off of it. So in this case, we have 1, 2, 3, 4. Zaitsev's rule says the more carbons that you have coming off of your double bond, the more stable the alkene product is. We can use this to predict our major product. Since this one has 4, unlike any of the other ones, for example, this one over here only has 1, 2, 3. The one with the 4 carbon substitute off the double bond is going to be our major product. Okay, but how does this happen at the molecular level? What's going on here? Introducing the Sn1 Mechanism! Let's have a look. It should be noted, I'm only going to show the electron pushing for the major product, but the minor products, if you can do the electron pushing for the major product, you'll have no problem with the minor products. It's basically the same idea, except you're pulling off a different proton at the end. So, how do we get there? First of all, a nucleophilic attack. So, the first step of all 4 of these reactions is going to be a lone pair from our alcohol attacking a proton. So the proton can't take 2 bonds, so these electrons will jump onto the oxygen here. This is going to be the first step for all 4 of these reactions that we're looking at. What will that leave us with? This, our protonated alcohol intermediate and bisulfate. It will be coming back later in the reaction, but for right now we're going to say bye bisulfate. It'll return eventually. So, what happens next? Well, next, because this proceeds through a carbocation intermediate, we have to look at our water here. What is significant about this water that we're making in all these reactions? Well, water is a good leaving group. That is why it's significant. So that's why we're always going to start by protonating that alcohol. So, in this particular reaction, the E1, the next step is the leaving group makes like a leaving group and, appropriately enough, leaves. So, that gives us our carbocation intermediate. So now we have our carbocation intermediate. Oh. Okay, so now in order to form the most stable product, we need to do a hydride shift. Now, this tertiary carbon adjacent to the carbocation, remember it has a hydrogen that's not explicitly drawn in. So the hydride shift is really a pretty simple case of electron pushing. It's just these electrons jumping over here and taking the hydrogen with it. So that will give us, so here we have our tertiary carbocation intermediate, and we are one step away from completing this mechanism. So remember our friend the bisulfate that we said bisulfate to earlier? Guess what? It's back and ready to react. What does it react with? Well, once again, adjacent to our carbocation, we have a hydrogen that wasn't explicitly drawn in here. But for this step, we need to show this hydrogen because the bisulfate is going to act as a nucleophile and it's going to grab that proton. These electrons have to go somewhere, so they're going to collapse down and form a double bond, which will lead us with our alkene product. And in grabbing onto that hydrogen, the bisulfate became sulfuric acid again. It was regenerated. That's how catalysts roll. Now, this H2SO4 can go catalyze more of these reactions and help turn more alcohols into alkenes. Okay, that is the mechanism to form our most stable product according to Zaitsev's rule. Now, let's look at a different reaction. An alcohol, H2SO4 and heat, this must be an elimination reaction. Okay, well now let's look at our alcohol. Here we can see it's primary. So, this means we're going to be looking at an E2 reaction. Okay, so predicting the product of an E2 is pretty straightforward. Essentially what we're going to do is draw the exact same molecule we had to begin with, like so, without the OH. And, actually, just as a quick note, sometimes counting carbons using, in this case I'm using the benzene ring as a placeholder here, is really helpful because you can make sure you've got the correct number of carbons in your product. So anyway, we draw essentially the same thing, only without the alcohol, for you see it was eliminated, and when we do an elimination reaction, we end up getting an alkene. So, that's going to be our product, our sole product in this reaction. And for our purposes, all these E2s are only going to lead to one product. I suppose for posterity's sake, I should draw the product in the product box. Okay, well, how does this happen? Let's go to the E2 mechanism. Let's begin. So, first things first. What's the first thing that always happens with our alcohol reactions, be it Sn or E? Well, the first thing is our nucleophilic attack. The alcohol is going to be protonated. Why is that? Well, it forms our protonated alcohol intermediate with the really, really, really good leaving group in water. So, what happens next in the E2 mechanism? Well, just like before, in our first step we formed bisulfate, which is ultimately going to grab onto a proton. And what's going to happen here? Well, here we're going to do our elimination and alkene formation in one foul swoop. There's no carbocation intermediate. So remember, there is a hydrogen not explicitly drawn in here. And what's going to happen is this is going to grab onto that hydrogen. This is going to collapse to form the double bond. And our leaving group is going to make like a puzzle in piece. And that's going to give us our alkene product with the H2SO4 regenerated, so it can continue catalyzing things. Okay, well, what's next in our reaction repertoire? Well, here we're reacting an alcohol with HCl. So when we see HCl and alcohol, we want to think, oh, okay, well, this is not going to be an elimination. This is going to be a substitution, an Sn reaction. Further, this is a primary alcohol, which means this will be Sn2. Okay, so how can we predict the product? Predicting the product of an Sn2 reaction is really easy because we're just substituting out the alcohol with whatever halogen is in our acid. So our product is going to look like this. Really not bad. Let's see how this happens. The Sn2 mechanism! Alright, how does this begin? Well, you probably see a theme developing here. It begins with a nucleophilic attack of our alcohol onto our acid. These protons jump off, and we're left with our protonated alcohol, our water leaving group, and chloride. Okay, so up next, remember that what makes the E2 and the Sn2 reaction unique from the E1 and the Sn1 is that there's no carbocation intermediate formed. Instead, this next part of the reaction takes place in one foul swoop. So the chloride is going to attack the carbon that is holding onto the water leaving group, and the water leaving group is going to, appropriately enough, leave, which will give us our product with a chlorine now instead of an alcohol, and water is going to have left the molecule. Speaking of water having left the molecule, I want to quickly go back and note in this mechanism I should have included that water is given off as a product in this reaction. My apologies for not including that earlier. Let's continue. Alright, let's look at one more reaction type. So, how do we evaluate this? Well, once again, we've got an alcohol reacting. We've got HCl. So, since it's HCl as the reagent, that means we're going to be looking at an Sn reaction. Same thing with HBr and HI. And then we just needed to check what type of alcohol this is. This is a secondary alcohol. Remember, a secondary or a tertiary will go through either an E1 or an Sn1, depending on what reagents you use. Okay, this all comes down to our intermediate, just like our E1 reaction. So, once again, very helpful to draw out what the carbocation intermediate or intermediates look like. Let's do it. Here's what the initial carbocation intermediate would look like when the water leaves. But hark! What's this? Adjacent to the secondary carbocation is a tertiary carbon. That means this is a candidate for a hydride shift. Let's draw that intermediate too. Okay, there we have it. And then, once we know the intermediates, the product is really easy to predict because all that we're going to do is put chlorines, or whatever halogen you happen to be using with your acid, at the site of your carbocation. So here and here. The more substituted one, the more stable intermediate is going to lend itself to the major product. So our major product will look like this. And our minor product will look like this. But how does this happen? Let's take a closer look at our final mechanism of the evening, the Sn1 mechanism. Let's do it. First things first, how do these all begin? That's right, it starts with this. Attack on the hydrogen, and then whoop, this jumps over. So we get our first set of intermediates, or organic molecule with the water leaving group and chloride. Okay, so because this is Sn1, remember that what happens next is this lends itself well to forming a carbocation intermediate. So the next step is this is going to leave. So here we get our carbocation intermediate. As I said before, I'm only going to show the mechanism for how we form the major product. If we wanted to, we could just have the chloride attack the carbocation right here, right now, to form our minor product, but let's show the hydride shift that leads to the major product. So remember, there's a hydrogen on that tertiary carbon, and we can just have the electron swing over to that site, giving us this. I also want to point out that drew in the water, remember when water acts as a leaving group, we have to depict it as having left. Okay, and then how does this reaction finish? Well, that chloride from before, that's better. It's going to act as a nucleophile and complete the substitution. So it's going to attack the carbocation site to give us our major product. Okay, well that concludes this look at the Sn1, Sn2, E1, and E2 reactions and mechanisms with alcohols. Hope that you found this video to be useful. If you like this video, remember to like and subscribe for more content like this. Thank you very much and have a great day.